Okay, let's go ahead and get started. Welcome to OM 680 Decision Analysis and Risk Management. My name is Bill McKinnon. I am Assistant Professor of Information Systems in the School of Business at Clarkson. And we're going to jump right into the first chapter of the Baker text. We have two texts for this class. One is Baker's text on spreadsheet optimization, and the other is a few chapters from the Powell and Baker book from Management Science, and you will get that electronically. You can check your syllabus for the details of that text. We're going to take the chapters pretty much in order, starting with the Baker text. And so let's go ahead and get started on Chapter 1, Spreadsheet Models for Optimization. So this chapter, and actually much of the course, is about modeling, okay? And so that brings up the question, what is a model? Now, so when we say the word model, what are we thinking of? Are we thinking of this, or how about that? Well, in fact, those are models, okay? What is a model? It's a representation of something, a person, place, thing, situation, problem. All right. And so obviously, we're not talking about these three particular types of models, but the point holds is that we create models for the purpose of understanding something, of simplifying something. Okay. In our case, we want to be able to achieve understanding and the solution to particular problems. A model can be constructed of materials, words, mathematical expressions, and of course, even people. But we're going to be talking mostly about spreadsheet models, okay? And this is where we take an unstructured type of problem and structure it in a spreadsheet for the purpose of decision analysis. So a spreadsheet model contains all of the elements of the model, and we'll get into that more deeply as we go along. But basically, we try to put all that we need on the spreadsheet, all of the data, all of the calculations, so that not only can we find the answer, but we can communicate the answer. Okay? And so all of these elements of the model are linked together logically. Okay, so you should be able to look at a model with some practice, look at a spreadsheet model and say, I understand, I recognize all of these components and how they are linked together. Much of this class is concerned with optimization. Okay, and so that brings up the question, what is optimization? Optimization is finding the best value for a variable or a set of variables. We call them decisions. We want to make the best decisions that we can for some particular purpose. And that purpose is usually to achieve an optimal measure of performance. Now, the measure of performance may be cost, for example. And so typically an optimal cost would be the absolute minimum. Or maybe the measure of performance is profit. So in that case, the optimal value would be the absolute maximum. Okay, so we want to take a look at the things that we can change and change them in such a way as to achieve the best possible performance. Okay, now there's always a but, and that usually comes in the form of some kind of constraint. So, for example, if we want to minimize travel costs, we could do that by not ever traveling, right? But that's not realistic, okay? So suppose our constraints or our criteria are that we have to travel to points A, B, and C and minimize our travel costs. So the constraints are we must visit A, B, and C. And so we get into the decisions about the best routes or timing to visit those places and achieve our minimum travel costs. Likewise, with profit, we could maximize our profit by selling a bazillion items, right? But normally we can't, that's not realistic. Our constraints are often supply constraints. You are constrained by the amount that a factory can produce for example. So normally, not in every case, but normally an optimization problem in a spreadsheet or any type of optimization problem will be subject to certain constraints. So what are the elements of a model? We're actually going to talk about two types of model here: algebraic models and spreadsheet models. All right, this is not a math intensive class. Okay, we assume that you have some statistics. All right, and we'll need that a little bit. Okay, but for the most part, we use algebra. Okay, and most of our model building is based on algebra. And in fact, we don't always. We skip right over the algebra as we get more used to doing these types of problems, and we start just building the spreadsheet model automatically. But always behind it, the logic behind it is usually algebra. Okay, so let's take a look at an example. All right, and this is a typical demand example. Okay, so suppose we have the cost of a particular product is $40. That's what it costs us to produce it. And we know the relationship based on perhaps historical data. We know the relationship between the sale price and demand is y equals 800 minus 5x, a simple algebraic expression that is a typical demand curve. Okay, y is our demand, x is our selling price per unit. We'll introduce another variable that is z. Z is our profit. Okay, that is our price minus our cost times the demand. All right, and then we can continue to work through the algebra until we finally get z equals 1000x minus 5x squared minus 32,000. Okay, we don't even necessarily need that algebra for the problem. Just maybe want to give you a little bit of a refresher on how algebra works. Not everybody uses this every day. It's not hard, but you may have to practice with it a little bit. So continuing on with the elements of a model, the elements of a spreadsheet model first are parameters. Okay, this could be historical data or some kind of estimates based on historical data. In our case, we have three parameters in this example. One is $40. That's the unit cost. Minus 5 as part of that demand curve equation is the slope of the demand curve. In other words, it's the marginal effect of price on demand. Now, it has a negative number. So what does that mean? The marginal effect means that if our price goes up by 1 unit, in our case $1, demand will go down by 5. Okay? So for every dollar price increase, we would expect our demand to go down by 5. And that's the meaning of the negative sign. Okay? And if our price was 0, we would expect to sell 800 units. That's our maximum demand. Okay? So these are the parameters that make up our little cost curve. Now, we have a decision to make. All right. In this case, it's only one. What is our optimal selling price? Okay. Price it too low, price it too high, and we don't get the maximum profit. Okay. So we want to find the price that gives us the best profit. Okay. Our objective is to maximize profit. And normally, in terms of spreadsheet terminology, we would call these things data, decisions, and objectives, okay, or objective. And so we want to maximize profit. So we also, in a spreadsheet model, I said we have inputs. I don't call them inputs. I'd rather call it data. We have decisions. Sometimes we have an area for calculations. Not always, but sometimes. And then we have outcomes. And again, I'm going to require a certain type of form for the problems that you do. And so in the form that I'm going to require that is very standard, we're going to call it the objective. Now, I'll become more strict about the form as we go along. I'm not going to worry about it too much in the first homework, but then we'll get more formal as we go along. So here is the spreadsheet model for our example. Okay, we have our inputs. Again, you could call them data, you could call them parameters. I prefer to call it data. I'm following the book here, but he's not always consistent in the form that he follows as well. So I'm going to ask that you use data instead of inputs, decisions, calculations, and outcomes. And again, as we go along, we're going to require you to call this the objective. All right. Notice that the numeric parameters are placed in cells rather than burying them in equations. The novice Excel user or person that's doing optimization will simply embed these in the calculation somewhere. We don't want you to do that. We want you to put them out there where people can see it. A couple of reasons for this. It makes the model more understandable, all right? And it allows us to change these parameters if we wanted to reuse the model, okay? And so we can refer to these cells in our calculations rather than embedding those numbers in our calculations. And that's going to be important, all right? Because the tendency is to just care about the right answer. But spreadsheet modeling, optimization, decision analysis is so much more than just finding the right answer. Okay, it's how you find and how you communicate your results. And then we have our decisions. Decisions are usually highlighted in yellow, and our objective is highlighted in green. Okay, again, this form allows you to look at a spreadsheet model and quickly recognize what's varying, what you're trying to optimize. So this is going to be important. Now, as an alternative, this is an alternative model that achieves the same results. Okay, we now have price and demand as decision variables. In other words, we let the optimizer figure out the values for these. Okay, and our maximum demand becomes a constraint. Okay, constraint means that in this particular model, demand cannot exceed 800. Okay, so no matter what price decision that we get, the optimizer will keep it so that demand never rises above 800 because we have determined, historically speaking, based on our historical data, that demand, even at a zero price, demand simply won't go above 800. Okay, and so both of these models will achieve the same result. But the key here is that you can look at it and again, with practice, understand what's going on, and you could take this and communicate it to the other stakeholders. So there is a hierarchy for analysis. Okay, the first thing that we do is build the base case. Before we ever run the optimizer, we build the spreadsheet and test it. Okay, basically, you build the spreadsheet as if you were going to put your own numbers in those yellow cells and try and figure out the solution through trial and error. Okay, and anything that you put in those yellow cells, the result that it produces are called feasible solutions. In other words, this is a solution that could happen. But we're not just looking for a feasible solution, we're looking for an optimal one. So we can find the optimal one by asking a series of what if questions. And in fact, Excel has a what if analysis function. It's called the data table, and it can be very handy. All right. And that is what we call a sensitivity analysis. In other words, we change something and see what happens to our objective. All right. What we're trying to figure out is how sensitive our objective is to changing certain parameters, for example. And in some cases, we'll find that it's very sensitive. In other cases, we'll find that it's not at all sensitive. There is also a feature in Excel called goal seeking. So, for example, if you wanted to do a break even analysis, in other words, at what point, at what set of decisions does our profit and our cost become, not our profit, our revenue and our cost, at what point do they equal? Okay, and so we could do a goal seek. We could set profit to zero and ask Excel to figure out the right set of inputs to see where our profit is exactly zero, and that's our break-even point. But a lot of this can be trial and error, okay? And depending upon the size of the model, it can be very time consuming. And really, when do you ever know if you found the optimal value? Okay, trial and error is fine. It allows you to help find some feasible solutions, but unless the model is very small or you're very meticulous, it's hard to be sure that you found the optimum. So that is where optimization analysis comes in using Excel's solver function. Okay, it is a robust and sophisticated form of sensitivity analysis. Essentially, the optimizer does the trial and error for you. Okay, it runs through all of the possible combinations and it finds the optimum. All right, and then it returns that value to you. And it's much, much faster. It allows for much more confidence that you have, in fact, found the optimal solution. So now let's take a look at using the Excel solver. That's our optimization program that's built into Excel. All right. In optimization terminology, what we want to do algebraically is maximize Z. That's our total profit by Z equals your unit profit times your demand. Okay. Subject to y plus 5x equals 800. Now, this is just our demand curve, just reformulated a little bit. We've taken 5x from the right-hand side and moved it over to the left-hand side. This is normal. Normally in optimization in Excel, we want on the right-hand side of the equation only a parameter, only a number. Okay? We want all of our equations and our unknowns to be on the left-hand side. Okay, in terms of spreadsheet terminology, we want to maximize C16, okay, by changing C9 and 10, subject to this constraint, okay, so that the demand curve is satisfied. So our C13, when we find the optimal price, will equal 800. Okay, and that's this. So this is our base case. All right, we have set up the spreadsheet so that it works. These are not optimal solutions. They are simply feasible solutions. We know they're not optimal because 650 does not equal 800. All right, but now we know that the calculations work and we have our base case set up. So now we move on to solver. Okay. If you go to the data tab, if you have the add-in enabled, go to the data tab, click on solver, and this is what comes up. Okay, the first thing that you see is the objective. Okay, that's the cell that we want to either maximize or minimize or set to a certain value. All right, typically we're going to want one of these two. In this case, we want to maximize it. We have to tell it what cells are changing. These are going to be our yellow cells. All right. And then finally, it is subject to certain constraints. Cell C13 has to equal cell E13. Okay. Now down here is what algorithm solver uses for its calculations. And in this case, this is a nonlinear function, so we'll use nonlinear. Don't worry about what that means right now, okay, if you don't know. So when we add a constraint, we get a second dialog box. All right, and so this is where we say that cell C13 is going to end up equaling. This could be less than, or greater than, or equal. We can also specify that the values are integer or binary. Okay, but this is where we do it. All right. So again, we have formulas on the left hand side. We have numbers on the right hand side. That's the way you do optimization. All right. Our objective is C16. Our variables are C9 and 10. Our constraint is that C13 must in the end equal E13. Now, let's summarize. This is a short chapter, but that's okay. It's a good introduction. And I've given you 5 or 6 homework problems to work on so that you get used to doing this. Optimization is about extracting an accurate model from a word problem. Okay. I like to put it this way: we take an unstructured problem and we structure it. All right. That's what a model is. And we ask the questions: what are we trying to optimize? What decisions are open to us? In other words, what can we change in order to achieve our optimal result? And equally important, what constraints are we subjected to? Do we have capacity constraints? Do we have to meet a certain level of demand? Do we have time constraints, and so on? This second major bullet here, I can't emphasize this enough because I see this a lot when students turn in optimization problems, like in homework. They are their ultimate worry or their ultimate goal is to achieve the right answer, and they don't care how they achieve it. Okay, that's not acceptable. All right. Good spreadsheet form is as important as finding the correct answer. I absolutely want you to find the correct answer. Okay. But I want you to do it in the correct manner. All right. There are a lot of different ways that you could formulate this really ugly, unintuitive ways and come up with the correct calculated answer. All right. But that's not the whole point. The whole point is not to find the correct answer. It's to find the model, a good model that will allow you to find the correct answer. Good form allows us to understand the problem more easily. Good form allows us to alter the parameters easily so that we hopefully can reuse some of these models. And lastly, good form allows us to communicate the results easily. All right. Sometimes these solutions will not be for immediate implementation. They're simply planning models or what if. And so it isn't like we're going to find that optimal price and immediately go and change our price. All right. Maybe we will, maybe we won't. Okay. And so we need to be able to show this, communicate these results to the various stakeholders and perhaps change things around. And so that is, I'm going to stress this a lot throughout the semester. Good form is as important as finding the correct answer. And in fact, in terms of homework and exams, bad form will be penalized more heavily than incorrect answers. Okay, you can always make a little mistake somewhere, even with a good, well laid out spreadsheet, and not find the right optimum. All right, and yeah, you'll get a penalty for that. But it will not be as high as you give me some horrible monstrosity of a spreadsheet that has the right answer. Okay, so make sure you focus on form. That's it for this chapter, and hopefully you will listen to this before our first synchronous session. So I will talk to you on Thursday.